my first experience with Scheme was something called Dr. Scheme. That's a long time ago. People won't talk about that anymore.
God, you
but when I went to grad school at Indiana, I also used a system called Chez Scheme, and so to this day, I keep going back between a system called Racket and a system called Chez Scheme. But now maybe we can have kind of both together. And so this reminds me of something Andy Lumsden would always talk about, where two great things that go great together. So we're going to learn about Racket on Chez. Thank you, Matthew. Thank you.
There's a color scheme to the talk that it may help to know up front. I'm going to use blue to mean Racket the language, and also Racket on Chez Scheme, which is largely implemented in Racket, as well as Chez Scheme. And Racket CS probably won't show up much, but that's like the executable name of Racket on Chez Scheme right now. I'll use red to mean the C programming language, or sometimes for Racket, the old implementation or the current release, which is largely implemented in C. And then when I need to refer to Chez Scheme, I'll use purple for that. So not a big deal if you don't get that, but it might help as we go, because I'll be talking about several languages, several implementations, all at the same time. Here's what Racket version 6, the distribution looked like. So version 6 would be the one just before right now. There's the core implementation, that's in red. Remember, that's C. Collects, that's kind of the libraries that are part of minimal Racket, the minimal thing you can download, install to get other packages. Then if you get the regular distribution, you've got a bunch of packages. Included in those packages are documentation, which are in a variant of Racket called Scribble. So all of this blue and green stuff, great. What we're going to talk about is the red stuff down here. So let's zoom in on that. We're talking about 230,000 lines of C code or so. Totally fictitious layering of the system would look like this, right? It's actually there's lots of dependencies between things, but you can kind of break it out into these major subsystems. In contrast, here's Chez Scheme. So Chez Scheme is a lot of scheme code on top of a small C kernel. So the kernel is going to be garbage collection, I/O, glue to the operating system, and so on. So you can see why we're going to go from here to there. Why Chez Scheme in particular? Well, first of all, it's a scheme, and that's an obvious choice if you don't think about it. If you think about it a little more, there's a lot of other runtime systems and compilers out there that are built to support multiple languages. But if you think about it even more, well, any scheme is going to have the right kind of number system and continuations and lambdas and be tuned for the way that Scheme and Racket programs look. Continuations, especially on Chez Scheme, are a good fit for Racket. Racket needs delimited continuations. You don't get that out of the box with Chez Scheme. But because Kent and his colleagues, they were looking at delimited continuations before I knew what Scheme was, the right kind of hooks are there, and it was easy to get it out of Chez Scheme. And also, the Chez Scheme manual is very careful not to promise any sort of space safety guarantees, but in practice, it's put together in a way that's very careful to not retain memory unnecessarily. That's an important property for Racket. Things fall over if the language doesn't behave in a space-safe way. So for all of those reasons, I skipped on-the-fly compilation. That's another part of the culture. More generally, it's because we imitated the way that Chez Scheme works when we started building PLT Scheme way back. Just the idea you don't explicitly compile your programs, you just start evaluating them and they get compiled on the fly. So it seems like a good fit. If we look on the inside of things, why is this so much shorter than this one to start with? It's not just because it's in Scheme, it's because there's less stuff that you get out of the box, right? So we have to add a whole bunch of stuff in the box. I'd say the built-ins is smaller, mostly because that is more compactly and nicely implemented. By built-ins, I mean vector ref and plus and car encoder and so on. The compiler is a bit bigger because, well, this is what Kent and company do. They build compilers, and it's a much more sophisticated compiler, even if you roll in the JIT part of Racket. And this tiny little sliver at the bottom, that 2K, that's the garbage collector, compared to Racket's 11K. That's definitely a feature because, as you'll see, I have to modify the garbage collector a bit. So we'll just ignore that from now on, though, and just treat it as a blue box or a purple box. This is what it looks like when you build Racket on top of Chez Scheme. So, of course, you start with Chez Scheme. There's a layer that adds control and structs. What I mean by that is Racket structures, records you would call it, perhaps. They have properties on them, so there's some extra bells and whistles there. And proxies, chaperones and impersonators. And building those closer down to the core makes things perform better. We call this Rumble, just to give a name for that layer of things. I don't think the name comes up, but I put it there. On top of that is then Racket's green thread system, so that is now implemented in Racket. It's called threads, but really it's mostly about events and synchronization and concurrent ML style synchronization primitives. On top of that, we have the same Racket IO library that we have over here. If you're familiar with libuv, as used in Node, it's that kind of thing. It just has exactly the right things that Racket needs and has been around for 20 or so years. So we just package it up. It's the same kind of thing that's written in C down here in the Chez kernel. It's just we need a broader interface to the OS. But then there's an IO layer on top of that, which gives you the Rackety layer of IO integrated with events and threads, and so on. Finally, there's the big chunk at the top, the expander. That's the macro expander, the module system, the compiler from the module expansion down into the underlying substrate. So this is what people ask me for the last couple of years. Does it work? Well, of course, I am running the talk in the new system here, right? So that's Chez Scheme. If you want to run it, you can too. Just clone the Racket repo and go into that directory. Normally, you just type make and wait 45 minutes, and you would get regular Racket out. Now type make CS, wait, well, we'll see. And you'll get Racket CS out, including Docker Racket CS. In fact, I'm not just running this talk in slideshow on Chez Scheme. I'm running it inside Docker Racket running outside of Chez Scheme. So things generally work. This little green dot, just a super important green dot. That's background expansion running in a separate place, running in parallel, you know. So that's an indication that most things generally work. You know, you see the arrows. Okay, so you can actually run it. Now I can crash this very easily. I know how to make a WAN character change and it'll crash, so it's not quite ready for you to use every day, but you can try it out. Let's get this out of the way. You want to know how much faster it goes, right? So these are the traditional standard scheme benchmarks. I've broken them up into two groups. The ones in green down here, these use mutable pairs, right? The ones above that don't. So the ones above sort of run as Racket programs, whereas these need an R5RS compatibility layer. That'll be relevant to the performance. What you see, I've also sorted them by Chez Scheme being faster than, actually Racket on Chez Scheme being faster than Racket. And you can see the break-even point is pretty far down here, actually somewhere around here. Right? So mostly, yes, things run faster on traditional benchmarks. The important thing about this plot actually is how much changes between the purple and the blue, because you already knew Chez Scheme runs traditional scheme benchmarks faster than Racket. What you want to know is, have I messed it up by putting this Racket on Chez Scheme layer on top of it? Mostly, no. There are some places where I need to look more closely to see what's going on, like Scheme 2 there. But mostly, we're preserving the benefits of Chez Scheme for these kinds of benchmarks. Not so much down here. The reason these blue bars are all bigger than the purple bars is because mutable pairs means you're not using regular cons. You're using a separate mutable pair data type. I don't care about these because Racket programs don't use mutable pairs. Right? If you wanted to run Scheme programs, you would just use Chez Scheme. Shootout benchmarks. So these are a lot more than you'll find on the Shootout page now, but over the past, I don't know, many years, there's been a collection of benchmarks that have run through there, and we've gradually accumulated a bunch. What you see here is the break-even point is much earlier, and that's because these benchmarks are written in a more rackety way. They're not pair and lambda benchmarks, roughly speaking. And so they're more representative, perhaps. So the bottom line is Racket on Chez is not a project to make Racket faster. I am sorry, right? So it's going to run reasonably well, but you should not expect things to magically get faster. So why do this? Well, why do this is because things become more maintainable. And in fact, if you look at this picture, you know, you can imagine that there are some dependencies between the layers, but there's the expander box sitting pretty much on top in both cases. Why not take that blue expander box and put it on top of the Racket 7 core? I mean, without doing a whole bunch of work, that should be better already. And yes, that is better already. That is the current release, the Racket 7 release. So that has encouraged us that it is really worthwhile to both rewrite the code in a better way and put it into Racket and Scheme to make it more maintainable in the long run. All right, that said, I'm going to show you various performance slides because it's all about making everything run practically. And I feel bad about that because at the end of the day, it's not about performance. It's just about making the transition practical. Let's see, let me remind you. We're talking about a single expander now running in both systems, compiling down to the next layer, right? So you've got a module, and the expander's job is to do all the macro expansion and flatten that module out in some way that it can be sent to the traditional Racket implementation and the Chez Scheme implementation, right? So what is it that these modules compile down into? Everyone here knows the answer. What is it? Oh, no, it's Lambda. Okay, it's not actually Lambda. You would think it would be Lambda, and it's almost Lambda. It's this new construct we introduced called Linklit, which is a slight variation of Lambda. Unlike a Lambda, Linklit has imports and exports, and these are variables, mutable variables, potentially mutable variables that come in and go out. And that's because in Racket, you can mutate a variable in one module, and the mutation is visible in the other module. Right? Not what you want to do most of the time, but we do support that. And it's helpful to kind of expose that information potentially down to the next layer of the compiler to get good performance. Similarly, the body here is a sequence of definitions or expressions. The exports here are drawn from the set of defined things. So it's a kind of minimal modularly tweak to Lambda. Yes?
Does the let mean let or small?
Small. Yeah, because it's a piece of a linkable thing. Yep.
So if this is done for performance reasons, I assume, right?
Yes.
Will this be exposed for people who want to go fast and dangerous, or is this like hidden underneath layer?
No, you can use the Racket/Linklit library gives you these functions that I'll show you in a moment.
Oh, cool.
Yeah, so you can get to it directly, and that's kind of the foreign function API to get down to Chez stuff, because Linklits are giving you the raw, almost the raw Chez level. Almost, but not quite. Almost, but not quite, and it's not quite because this is kind of a minimal module layer for the underlying compiler. There's a whole bunch of administrative work to link modules together, to break modules into phases, to optimize across module boundaries, and that's the key thing here with Linklits. So the Racket's traditional compiler, it knows about cross-module optimization. Now it knows about cross-linklet optimization. That's part of the API. There is a schemify pass that takes linklets and turns it into an actual Lambda, and that's what we send off to Chez Scheme. But schemify does some extra work to try to transform this in a way that's friendly to Chez Scheme, that the Chez Scheme compiler can recognize in a good way. And I'll talk a lot more about those details. The API that goes along with this is compile linklet, where you give it one of these S expression forms, and then a debug name. This import keys get import. Get import is a callback. So that is how the macro expander module manager collaborates with the underlying compiler, or really the schemify layer does, to help it. I shouldn't say really the schemifier. Let's back up. Let's just say that's how the expander collaborates with the compiler to give it information to do cross-module optimization. Okay? And then options is boring. Instantiate linklet is kind of like calling a function. That's taking the linklet and turning it into an instance. It's a pretty generic term, but it wasn't used yet. So an instance is basically a hash table mapping names, symbolic names, to these potentially mutable variables. And then to Bootstrap, to get things going, the macro expander can just synthesize some of those instances directly and fill it in with the primitives. Right. So those are the pieces. That's how we get interoperability, well, to make this expander work on different runtime systems. If you have your own scheme system and you're interested in putting a Rackety veneer on it, you just want modules and macros, you can just take this expander and reuse it by filling in this API roughly. There's a little bit more to it, but that's pretty close. So if you have a Racket module like this, here I've got a macro definition, some runtime code. This actually turns into a collection of linklets. And these two linklets represent different phases. So this is the runtime code, which you might not need at all. I mean, which might be the only thing you need if you're just running the final program. This is the compile time code, and Racket's module has this phase, module system has this phase separation. So we might multiply instantiate the compile time part multiple times and the runtime part multiple times, and they're kind of independently instantiated. And then it turns out to be convenient because syntax literals like that expression there, random1, sort of have existence across these phases. They get shifted depending on which phase you're using them in, but that's why there's a separate linklet for those. There can be more linklets if there are submodules inside of the module in the Racket sense, if you know what those are. then there's even more linklets that get generated. Okay? So the expander/module system is simplifying all of that phase management, as well as taking care totally of the representation of syntax objects and references across modules. In the body of the linklet, you may notice that we imported the random function, the library random function, but plus was just used directly. So linklets just refer directly to primitives. Again, that works nicely with the way the underlying compilers are set up. So all you need is about 1,450 primitives. Okay? So a lot of these things are all the math things. That takes up a lot of space. But there's all the list operations and the vector operations and immutable vectors and immutable boxes and so on. So that's the main obstacle that's why it's not running on Wasm already, right? Because we haven't implemented the 1,400 primitives. Let me tell you a little bit about the Bootstrap. So these chunks now are implemented in Racket, but we're going to run them on Chez Scheme, so we have to expand them and flatten them out and schemify them. So as we've said, expander here, it's not just one module, obviously, it's 200 something, I forget. So a couple of hundred modules get expanded into a few hundred linklets. And the same thing for these other layers. Of course, all this happens by running this Racket code on itself. It's a self-hosting kind of deal. You get these linklets, and they could be separately instantiated and linked together, but if you know statically what you want, then you can just flatten those linklets down. So there's as part of the expander package, there's also a flattener in there that'll sort through the modules, find the linklets that you actually need from the modules, flatten them out to just the runtime code. And so all of the compile time code, the macro stuff, that just evaporates away because, of course, the macro expander doesn't exist anymore, so you don't need that runtime support. Right. So you get a flattened linklet, and then if you're going to Racket on Chez, you schemify that and get it to a lambda. Right, so schemify just further manages those definitions on the inside, turns it into a lambda that takes roughly box-like objects as the variables as arguments. That solves kind of the high-level problems, but now we're getting down to the inside of a linklet where still there are some differences between Racket and Chez Scheme, and we have to manage those differences. For example, left-to-right evaluation. In Racket, if you call the function h with the result of f and the result of g, f will be called first. Racket guarantees left-to-right evaluation. Scheme somewhat famously does not. So it's just Schemify's job to rewrite these things to force the evaluation of f to happen first. This doesn't seem to cause much performance penalty when I play around with enabling or disabling. Schemify is careful to only introduce as much as it needs to. Like it didn't bind g to another local variable. Chez Scheme's compiler would clean that up if it did, but part of making sure we get good performance is not making the optimizer have to work too hard on things like that. Also, I'm assuming here that h is some immutable variable. So Schemify, knows which names correspond to obvious local variable bindings or local function bindings and so on. So when it knows h is a constant, it's not going to rearrange that either. I mentioned briefly that structures have properties and all sorts of bells and whistles like that. So here, for example, is a record type invertible procedure which has a function and the inverse of function inside the record. Right? And it also has this property that says you can use an invertible procedure as a procedure. That means you can just take an instance of this and drop it after the left-hand side, after a left parenthesis, and it'll call that function. And of course, Chez Scheme does not have this built in. So, compiling this down to Chez Scheme involves turning that defined struct into a defined record type, or at least the same thing that this expands to, so that Chez optimizer pass recognizes that pattern and gives you good performance on records, registering on the side some side table, the extra properties, and then changing this call from just cosine star applied to something to extract procedure of cosine star, which will always give a procedure back, and then it can be applied to the arguments. You see that plus didn't get mangled here. There's no extract procedure around plus because, of course, Schemify knows that that will be a procedure. Once again, it's important to minimally insert these kinds of things. It turns out most Racket code, as most Scheme code, involves direct calls to known functions. So this wrapper doesn't fire too much. Anything higher order is where it's going to fire. And even when it does fire, the cost turns out to be reasonable. Racket has continuation marks. So continuation marks mean during the dynamic extent of this body expression, record that key is mapped to value in this continuation frame. Right? If you don't know what continuation marks are, you feel free to talk to me or John more later. Right? But this is, again, something that, as far as I know, no other language has, including Chez Scheme. As a first pass, you can simulate this using continuations. Don't read the code, but what it does is it grabs the current continuation and then literally compares that continuation to one that it may have grabbed before to see if it's already put a mark on this. And Chez Scheme has a notion of identity on continuation, so that works. This strategy is not bad, but it turns out that it was worth a factor of 3 or 4 on this operation for me to go in and change the Chez Scheme compiler. Right? Yes, it does. But Racket on Chez does not because of various wrappers that we add, right? So, and that's why we could do this. That's why on both levels we were able to do this simulation. But it's in pull request farm right now to add a primitive notion of continuation marks into Chez Scheme. And this is where we start saying change Chez Scheme a lot, actually. So immutable pairs, we don't have to change anything. Immutable pairs means when you do cons 1, 2, that pair will forever have 1 and 2 in it. That means that list can be a amortized constant time operation, which is handy for many purposes. We implement this in Racket on Chez by just not giving you setcar and setcooter. They exist under the hood. There's some runtime system. There are ways that the runtime system can't take advantage of the fact that setcar and setcooter will never be called, but it doesn't matter that much. So that was easy. But immutable vectors, not so easy. We just changed Chez Scheme to have a notion of immutable vectors. And that's because Racket does have mutable and immutable vectors. They both answer true to vector. They both work with vector ref. Adding a dispatch for that part on every operation would be too painful. Right? So Racket compiles literal vector, schemify converts literal vector declarations into immutable vectors. And Kent and the Chez Scheme people were happy to accept that pull request. It's already in the current Chez Scheme. And more like that. So compare and set operations for when you have multiple threads, easy to add. It's just to add access to those machine code operations. Ephemerons and finalization. There were several things in the garbage collector layer for finalization. Ephemerons are like weak pairs, only more weak. It solves the key and value problem. You can't get anywhere in Racket without ephemerons at some layer. So I changed the garbage collector. This is where that 2K-ness of the 2K garbage collector really was nice. It was very pleasant to change the garbage collector to add these things. Ordered finalization, actually a hard topic, but it was not easy it was not difficult to add. And I also had to make some extensions to the foreign function interface to do structure arguments and returns. So nothing you wouldn't expect, really. Okay. There are still some outstanding differences. CP0, Chez front end, will sometimes optimize a non-tail call into a tail call, which is great if you can't inspect the visibility of tail calls. But if you have continuation marks, you can tell the difference. So I have to find some way to disable those transformations or guard them so that they won't be detectable, as the old Racket optimizer did. My guess is that's going to be pretty straightforward, but I haven't tried it yet. Memory accounting is going to be another change to the garbage collector. So memory accounting is, in Dr. Racket, it doesn't say any memory limit here because it knows it's in a mode where it can't support memory limits. But when you normally run Dr. Racket, you can say, limit it to 256 megabytes so that when your program uses too much memory, it doesn't kill off Dr. Racket, which is running on the same VM. So that'll be another GC change. I think it'll be fine. Let me get back to the right place. Eek does not work on flow nums in Chez Scheme. I think we're just going to have to say Eek does not work on flow nums in Racket on Chez. So, because it's hard to get around. LetRec assumes that in Chez Scheme, LetRec assumes that you won't use call CC and return multiple times on the right-hand side. Real programs don't do that. Racket gives it a very specific semantics. I'm not sure. We may punt on that too, or maybe it'll be tractable to adjust optimizations to account for that as well. Not sure. F of I differences are going to remain. I mean, it's just fundamentally different allocators, different properties of the allocators. These bleed through when you're looking at it at the C level of abstraction. I've been able to smooth off the differences enough to run Dr. Racket, so that's probably good enough for most purposes. And extended precision floating point number is 80 bit floating point. We can just do it out. It's already optional, not always available in Racket anyway. All right, so, the list is short. It's getting closer. That and bugs are all we have to fix. All right, so a little bit more on performance and the ways in which that's still an obstacle. Remember, Racket CS is the blue bar, Racket is the red bar, shorter is still better. So this is showing you that CL here means load Racket base, which is kind of the smallest useful Racket language, from source. Don't use any precompiled files. Right? So if you're loading it from source, these numbers you can't see very well, but it's 3 seconds and 5.5 seconds roughly. Right? Why does it get slower? Well, because there's a real compiler in there now. So the gray part is macro expansion, and that's about the same. That says the expander runs about the same on Chez Scheme as it does on old Racket. But the brown part here is compile, and this brown part is still compile, but specifically just the register allocation pass of Chez Scheme. So doing real register allocation takes time. I don't think that's a surprise to anyone who's done compilers before. And just there's this tiny sliver here, which is Racket's JIT, which is why I think of the compile phase in old Racket as being just free. Right? Everything was macro expansion. And the compiler in old Racket is basically CP0 plus a JIT that is a fairly direct, naive JIT. Right? The difference between those is where you get your factors of 2 sometimes. Just to compare and just to point out, we had already taken a hit when we went from V6 to the current Racket 7. Remember, there was that big gray bar? Well, when we re-implemented the expander from C in Racket, that gray bar got about 50% bigger. And so that's the difference between old Racket and big Racket. No one has complained in the last 3 months. So,
Please complain.
we will keep trying to improve it, but it doesn't seem to be an obstacle to making progress in terms of the way we structure Racket. Right? I did do an intermediate experiment. What if we use Chez compiler less or use it at the last moment, like we do the JIT in old Racket? So the compiler takes a linklet and turns it into a bunch of lambdas wrapped with compile me when you get here. Right? And most of the codes that you generate when you're just loading Racket is sitting in a library that you're not using yet. And so that does improve things. It gets halfway in between. This turns out to be a dead end, though, for reasons that we'll come to momentarily. Let's talk about, that was compile time. My sense is that compile time, people would like compilers to be fast, but it's not as big an issue as I've compiled my program, now I want to run it. I type just Racket at the command line, how long does it take to come up? Right? So the point here is that loading is orders of magnitude faster than compiling, and I hope you expect that. Right? But I point this out because I'm going to show you load time graphs, which will take up the same amount of space. But remember that we've zoomed in 100 or 2 times. Right? So zooming in 100 or 2 times, Racket L without the C is loading Racket normally. So every module has been compiled to, these are bytecode files, these are machine code files. Right? And we're loading those in just to get Racket going. And the numbers here, we're in the 300 to 600 millisecond range. So half of a second or so, third of a second. This difference is enough to be annoying, right? You start up Racket and it takes 0.6 seconds instead of 0.3 seconds. And I think that is going to turn out to be the bottleneck or not to actually moving this into production. But I think that we will probably be able to do it anyway. And of course, maybe we can make some improvements here. Just to compare again, we were already paying some amount of cost here. A lot of this, some of this, at this level, 64 milliseconds versus 128 milliseconds, that was the expander itself being in bytecode form. That is JITted as you load and start Racket. Right? We don't have that issue now, and that issue goes away as you get to more realistic scales. Of course, as you start Dr. Racket as opposed to just Racket, we're talking about many seconds, and then twice as many seconds. So then you start to feel it. And in fact, one way that Racket gets faster is by not actually parsing all the bytecode that you ask it to parse when you start up a program. It does it lazily. If you use -D, it turns off that. You can see, just parsing the bytecode or loading all of the code you asked it to load is part of the difference here. Maybe we can do some more delayed loading of Racket libraries in Chez Scheme. So it's a possible direction. The direction of JITting did not help here, and this is why I think it's a dead end. So here what we're doing is we're loading in code that's not in machine code form. It's in some other kind of bytecode form. It's roughly S expressions that have been fazzled. And then compiling on the fly, except of course, if every time we compiled all the fragments you run from scratch, that would be way slower. But if we keep a database of fragments that I've already compiled and use that database, then you get pictures like this. But it's still just not quite catching up to machine code. So it doesn't solve this problem. People probably care less about compile time. So that's why I think this JIT experiment was a dead end. What happens when you put all this together in a bigger setting? This is when you type make after checking out the repo, right? And it's after sort of the core is built, all the part that we've been looking at. This is the rest, the collects and the packages boxes. Every orange line is when we start on a new package, except compiling this package ends up and going off and compiling type track it as well. And then type track it starts compiling that package. So the big white gaps, those are all packages that use type track it. The first one, because it's starting, sorry, Sam. But, and then the cyan part here is when we're running the documentation, the scribble docs. The green is rendering those. We have to do it twice, basically, to get all the, because there's cyclic dependencies in the documentation. And in fact, we have to re-render to resolve all of those cycles. So, you look like you wanted to say something. I was hoping you were going to say, oh, it's all faster next week. Yeah. Well, I think the bigger picture here is it's about 1 million lines of code. Why does it take it 2 hours? Why does it take us 2 hours to compile that much? Even in the old Racket, the fastest one we had, it was 47 minutes to compile 1 million lines of code. I think I should probably not be looking at the fine details of loading code and compiling code, but understand where we're spending all of our time. It's not like 1 million lines of C, right? This is heavily macroed. This is macro running through a tower 20 to 30 deep, right? Macros expanding to macros, expanding to macros. We know some of where the time is going. We know that type tracket is doing a sophisticated type inference of your program that the Haskell type inference engine couldn't solve, right? So we know where some of the time is going. But I think probably that higher level areas where we should be looking. 5 minutes, all right, good. So anyway, it used to be 47 minutes when we re-implemented the Racket macro expander. It went to 1 hour, and now Racket on Chez, it's 2 hours. So how often do you recompile Racket? A handful of people here all the time. Most of you never do. You would just download it. More importantly, more important than these difference in times is the non-difference if you scale up the pictures to be the same width. You would have a hard time seeing the difference between these two if I just flashed it up briefly, right? The peaks are in the same place. The lines are straight where they should be straight. They grow where they're supposed to be growing because it's accumulating cross-reference information. So this is another demonstration that really, really works. It's not hard to get this picture, right? This was 3 to 6 months to make these pictures match, right? That's the kind of work that has gone into it already. So that's why we're confident that we can actually, that this will be a real thing and not just good enough to run slides. We've already seen the Seesaw today, but here's the Seesaw again. Yes, we got slower builds and loads, but having a better implementation is going to outweigh that. And I've shown you a bunch of performance graphs that are kind of depressing after a couple of years of work. So I made up a performance graph that shows how much better Racket CS is. This is number of people who have been willing to modify the Racket macro expander. Over 20 or so years, it's been me and Ryan. And Ryan put just enough instrumentation in so that he didn't have to touch the rest, right? So there's macro separate good work. Whereas, grad students are happily hacking away and experimenting with changes to the expander and trying out new things over the last couple of years. So this is why I think it's going to be the right way to go. Popular request. So, works on Chez Scheme now. How about Webassembly? Yeah, sounds good. More practically, though, Pickett is benefiting from this. The obstacle is 1,450 primitives right now. mean, and it's because Chez Scheme is a scheme, and because Racket imitated Chez Scheme in so many ways that most of those overlap. But this number is actually, it's not quite right because it's counting some things that are coming from these blue boxes, these new Racket implemented boxes. And we can make more of these blue boxes. We can break up more layers of things that are currently all the way in the purple boxes, or certainly were in the red boxes before, and make our way in this direction, right? It's a step forward, a step in the right direction. So, I've shown that it's possible by running the slide presentation, but also the benchmarks are meant to show that it's practical. Chez Scheme is not magic. It didn't make all of my code go faster. It's merely very, very good. It made it possible to, and it's going to be practical to make this switch. Still a few steps away. Don't develop in Dr. Racket on Chez Scheme just yet. But I'm pretty confident it's Racket's future. Thank you.
Thank you very much. That's great. Before we do questions very quickly, a couple of final announcements. Just want to do a couple more thank yous. Thank you to Arthur for recording the Scheme workshop. And hopefully the talks will be online soon for many Scheme workshops. That's great. Also thank you to the workshop co-chairs from ICFP and the general chair, especially Robbie and David, for being patient with us. And just a reminder that we're going to have a group of people who will meet at 6 after the keynote at this hotel at the entrance. Okay, if you want to go and get some steam dinner. All right. Questions?
Ryan was waiting.
I didn't catch what was happening with the interaction between non-tail calls and continuation marks. I was wondering, I would think of continuation marks as being non-tail things since you're adding marks to the...
No, okay.
Can you repeat the question?
Yeah, so let me get to a slide where I can repeat. With continuation marks, sets key to value during the dynamic extent of this body. This body is in tail position with respect to the with continuation marks. And if you have nested with continuation marks, they overwrite each other when you have the same key. That's why there's a key value. So they expose whether you're in tail position or not. That's what it boils down to. Yep.
So you showed the CPU difference. I wonder, is there any significant memory difference between the
Well, so this graph, let's see. This is higher in the green than this. This is higher in the green. So there's a little bit of difference right now. I think this is mostly a question of tuning and improving some representation because it's not obvious to me why it should be different one way or the other. It's really remarkably similar in scale. So, yeah, but the newer one takes more memory. I think that's the way it usually goes. Yep.
Of those 1450 primitives, how many can you get if you input those 8 blue boxes?
I don't know. How many does Pickett get with more blue boxes?
Pickett has fewer blue boxes than Racket on Chez. So.
Okay. Yeah, I mean, to repeat the question in case anyone didn't hear, how many can we cover of these 1450 primitives with more blue boxes?
No, with the blue boxes you have right there.
Oh, these blue boxes cover 400 of them or so. But in exchange for a couple of dozen that aren't exposed to Racket level that are used internally as glue between the layers. So 400. Let's say 400.
Have you measured the performance of new Chez on new Chez?
Performance of new Chez on new Chez. We have not yet, you mean?
Chez with the additions.
Yeah, so Racket on Chez running Chez Scheme.
I mean compiling the new version of Chez on itself.
Well, I mean, it's doing that in the sense that these blue boxes are compiled by Racket on Chez to get the code for Racket on Chez. And so performance-wise, though, that was the question. Oh, yes. It's pretty much the same. It's twice as long. Yeah. No, in fact, I've looked at that a lot because that's what I was doing at first. So, yeah, factor of 2. And I should say we compile these and run them in unsafe mode 03, which speeds up compile time a little bit and runtime some. How many of the primitives are necessary to host the expander itself? That is an excellent question. I'm going to guess 500, because you need some numbers. I think by the time you actually want to load a module, you get another 200 or 300. Yeah. And if you're on the right platform, you know, it wants the OS call to check file system changes. I mean, those get pretty obscure. You can ignore a bunch of them at first, no? Yeah.
Remember on some of those graphs, the register allocator running with Chez was taking up a chunk of time.
Yes.
So I guess the question is, how important is that register allocator to the performance you get of your executable at the end of the day?
That's an excellent question. My understanding is the current Chez Scheme register allocator is relatively new, replaced a much faster one, but you get better allocation from the current one. So, you know, part of this whole experiment is I'm not really a great compiler writer. Why don't I trust someone who is? So I'm just going to say it's better. Must be better. Yeah.
Brian? Yeah, more question. You talked about how much larger native code is than bytecode. Does Scheme still exist? Is there a bytecode backend for Chez that could be used for back representation?
So a bytecode representation for Chez, I don't think so. I mean, it really wants to. It can run in interpreted modes, but no. But everything, the compiling to machine code is pretty deeply wired in there. If you're interested in the relative sizes of C code and Racket code and machine code, I have lots of stories to tell you, but we'll take that offline.
Just thank you, Matthew, one more time. And if people